Hello and welcome to another operating systems extra help video. Today I'm going to be talking to you about some kind of common solutions to problems. It kind of came to me this past week in class that a lot of students find this course to be quite difficult. I mentioned it in the afternoon section that I had a former grad student who said that the operating systems class was the hardest class they took in their degree. So I figure maybe I should try and break things down and try and make this a little bit more approachable, because at the end of the day, I do think that we're actually looking at some common solutions to many different problems, and hopefully we can break that down and make this feel a little bit more approachable. So following that feedback, I kind of did some reflecting, and I tried to figure out why I thought that operating systems was such a challenging topic for students. And I kind of came up with this idea. I think that it's likely because it's quite broad, and the concepts all rely on each other and are quite diverse. So we see a lot of different topics, and maybe without understanding each individual topic, you can't understand the whole picture. So perhaps the interdependencies of all these chapters we're covering make them hard to grasp. And the pure, scope of the course gives the students whiplash, right? We're constantly flipping between different parts of our OS. Yesterday we were talking about device drivers. Today we're talking about file systems. Tomorrow we might be talking about mass storage and hard drive scheduling. And so all these things feel maybe very broad and very disconnected when you kind of need to understand them all together to get the whole big picture. And so I thought I'd take a second here and go back to the big picture of operating systems, right? Like, what is our OS doing? And at its core, it's doing these two things for us, right? It's trying to manage our resources efficiently, and it's trying to provide abstraction to make the system easier for its users. And these core two things are really important for our operating systems. Now, when I say manage resources efficiently, right, that's us talking about trying to get the most out of our CPU. We're trying to make sure that, we can fit as many processes as possible in main memory. And when I say provide abstraction to make the system easier to use, here I'm referencing, we give this nice system call API that our users can engage with so that they don't have to actually touch the messy internals of resource management or any of the other many nice things our OS does for us. So at its core, these are the primary two things it'll do. And I found there's kind of three patterns that we see repeated throughout most of our chapters. I classified them as a lookup or translation, metadata bookkeeping, and abstraction and interfaces. So for lookup and translation, often the operating system is going to give some logical versus physical separation between some kind of resource that a process needs and how it's actually stored. And largely this is done for the convenience of the program and the overall efficiency of the system. But whenever we add some translational steps to our explanation as to what's going on, I feel like that's just going to muddy the water slightly further and cause perhaps unneeded confusion. So hopefully by defining it as a pattern, a reoccurring pattern, you can then when you I guess we're at the end of the course, so you're probably not learning that many new topics, but when you go back and study the topics, you can be like, oh, that's just a translation step, and kind of hopefully engage with the core purpose of whatever the chapter is about, and abstract away that that's a translation, that's just a common pattern, that's how we do these things. Likewise, for each major topic in the book, there's going to be metadata or bookkeeping structures. You can just think of these as generic data structures. Because our operating system's low level, these are actually structures in C, but we don't get that detailed in this course, so you can just consider them to be any kind of data structure. And then finally, abstraction and interfaces, right? In order to make our system easy to use, we provide nice interfaces for maybe the messy internals, all the messy stuff the operating system has to do. So as we go through the chapters, often you'll you'll see here's a nice interface we apply for the users. Behind the scenes, here are all the things we have to do to provide that nice interface. And these three patterns often reappear in many of our different chapters. So let's dive in and start talking about them. Okay, so our first pattern is going to be translation through lookup. In this pattern, really we're just starting with something we know, and we're using it to find something we need. And maybe it's worth noting that these slides are, not super refined. I threw them together quickly tonight, and I'm recording them kind of whispering to not wake my son. These extra help videos might not have the same level of polish as a lecture, but hopefully they do help you understand some of the concepts. So here I tried to list out just from memory all the different things that might use this translation lookup pattern. So we see it time and time again, right? Perhaps you have a page number and you're trying to find the frame number, and we use this thing we call the page table or a TLB. Or we have a file descriptor, and really we're trying to look for some file object, and we use the open file table to do that translation. Or perhaps you have a path name of some file you want to access, and that path name ends up being the thing you know to find the thing you need, which is the inode, right? In order to modify, to read and write to this file, we need access to its inode, and we can navigate the directory or virtual file system structure in order to find that inode. So again, PID, process table, PCB, interrupt vector table, pointer to the interrupt handler. All of these translations, they're the same pattern. And maybe the thing you have is something complex, right? Perhaps a path name is something complex. We have to navigate mounted volumes and directory structures. There's maybe quite a few steps to go from that thing we know to the thing we need. Or maybe it could be really quite easy. Right here we have a page number and we're looking for a frame number. A page number is, well, let's get into it. So at its core, generally, this is a pretty simple pattern, right? We're just doing some kind of a translation from one thing to something else. And it can seem scary when we try to layer on all the OS theory, right? We're talking about pages, we start talking about addresses, we start talking about bits, files and file systems and mounting directories and volumes. And, we start adding all this OS theory, and then all of a sudden this translation seems scary. But in practice, it's going to be fairly simple. So let's talk about paging, because paging was largely one of the scariest topics. Even with my last help video, students were still wanting me to talk more about paging. So I'm going to use it as the example for our translation pattern. Okay, so let's talk about paging, and maybe we'll take it from the top. Hopefully you can skip ahead if you already remember all of this. But at its core, paging is really not meant to be that scary. We have frames and we have pages. We're going to store our pages in frames. And so when we're talking about paging, we always had our page number and our offset. So a page was just some unit of data that was the same size as our frame. So often we might have 512 bytes to maybe 4K in each page, but the actual size doesn't matter. And just for depiction, right here I've shown a page that might have, say, 42 lines. Let's say we can write 42 unique things in this page. It's got 42 unique addresses. So maybe we can write one word on each of these lines. So here's our page. It has 42 unique addresses. So in order to tell which address inside this page, you need some number between 0 and 42, and that'll get you to the actual line number. So here our line number, you can think of it like our offset. And then we're going to have many pages in our application. So in order to find maybe one word written on a line, you need to know which page number it is and which line within that page. So the offset was the line within the page, and the page number is, which of these sheets. You can imagine we have a stack of sheets like this. But anyway, this isn't a lesson on paging. If you want more on paging, go see that other extra help lesson and maybe rewatch the lectures in class. But for the purposes of our video, I'm more interested in just talking about page numbers, because that's what we use for translation. And we need something for translation because pages, we store them in frames. So pages are in the logical address space. This is the world the CPU lives in. But in reality, we actually have these things called frames. And I don't want to dive down this rabbit hole too much, right? We've talked about this for many lectures. So I'm just going to move on to the next slide here. So our logical address space we have over here on the right in pages. This is the world our process deals in, right? So our process thinks the world starts down here at, well, often I would depict this as page 0, but I pulled this graphic off online, right? So maybe we have the first page, and at the start of the first page, we've got address 0, logical address 0. That's where our process thinks the code starts, or whatever, where its memory space starts. This will be mapped into some different physical location, right? And the whole point of having these pages was that we can store them in any frame. We don't actually have to store page 1 in frame 1. And that solved a big problem when it came to address binding. Because we want to run more than one process, and every process can't start from address 0, right? We show here our operating system lives there. So we want to be able to jumble these pages up and put them in any of the actual frames in memory. And in order to do that, obviously we need some kind of a mapping to know where our process is going to store its page, because page 1 can go in any frame. And I guess maybe I got ahead of myself here. I was going to do a little walkthrough, right? Okay, pages go in frames. Our CPU lives in logic land. It only talks in pages, right? So when we're accessing an address, it's going to try and get some page and some offset. So we don't have to worry about the offset. The offset's the same into the page or the frame. We'll just talk in pages. So our CPU says, hey, I want page number 4. But the MMU, the hardware, it lives in physical land. It doesn't live in logical land. It only talks in frames. So if you ask it for number 4, it's going to return frame 4, regardless of what process you're in. Well, the MMU is going to help with the address translation, but the whole point is the hardware here lives in physical land. So how are we going to do the translation between logic land and physical land? And maybe I'm saying land to try and be a bit silly because it's late, but really I mean address space, of course, right? So how are we going to translate? Well, it'd be really nice if we had something that said, well, okay, our page 0 is actually stored in frame 10. And page 1, well, it's actually stored in frame 27. And page 2, well, it's actually stored in frame 2. Hey, maybe we got lucky there. And so on, right? It would be really nice if somebody just told us where every page was stored. Well, that's what we do. That's called the page table. That's how we do this address translation. So we have this special thing that we use to translate the thing we know, which in this case is our page, to the thing we need, which in this case is our frame number, right? So a page table, when we presented it, I think a lot of students found that this was a scary concept. We're talking in tables. What does that mean? It's just an array. It's just an array where the indexes are the page numbers and the values are the frame numbers. We call it a table. I skipped ahead a bit far, but anyway, we call it a table because we usually present it like this, with the page numbers, the indices, written out on one side, and then next to them in a table we see the frame numbers or values. So we call it a table because this is how we deal with it conceptually, but in code, really you can just think of it as some array that holds numbers. And so if you want frame X, you just look at index X in our page table, and that'll give us frame X, right? I imagine you're very familiar with creating an array and finding a value within that array. That's all we're doing when we're doing these address translations from page to frame number. The scary parts are trying to layer on the OS ideas, right? But hopefully if we can kind of say, hey, this is the pattern, this is what we're doing, maybe the OS ideas don't seem so scary anymore. Okay, so before continuing, because obviously paging is a big thing we want to review, maybe an admission of simplification on the last slide, right? It's a little bit more in the page table. It's really not just one number. It's not an integer array. We have these things called page table entries. So each each value in the array as I presented it last time is actually a page table entry. And one of those things in the page table entry is the frame number. But here we might keep track of a couple extra things. Valid might be a Boolean flag, a 1 or a 0. That just means, is this a valid page number for our process? Is this an assigned page, or are we referencing outside of our assigned memory space? Because usually the number of pages in a page table is fixed for a system. So every process might get, in this example, 1024 unique pages in their page table, but they don't all use them all. So if it's valid, that means they have that page, and that's a valid page. If it's invalid, that means they've gone over their address space. That's not a page they're allowed to reference. And the operating system should step in and prevent them from being able to access it. This dirty bit, dirty just means modified. So it's important that we keep track of this because when we go to, let's say, we want to, now this is foreshadowing, I guess, a bit for virtual memory, right? When in virtual memory, we were swapping pages in and out dynamically from main memory. If we wanted to swap a page out of main memory and it had been modified, it was important for us that we go back to store it in our secondary store. But if it hadn't been modified, we don't want to do that extra write back step because that's just a waste of overhead. So this dirty bit was really talking about whether or not it had been modified. And then referenced, maybe we can start getting some fancier systems where we share pages and then it's less clear as to whether or not we're done with them. So perhaps we can keep a list of references or something like that. Anyway, this is just a little aside because paging was really one of the main topics you wanted to talk about. And I kind of changed it to this "Why is operating systems hard" lecture instead. Okay, so here's our pattern, translation through lookup, right? We start with something we know and we just use it to find something we need. And we're going to do it in almost all of our chapters, right? So, here's a bunch of examples I came up with off the top of my head, but I'm sure you can find more when you're studying for your final exam. Let's get on to the second pattern. So we said our operating system was responsible for efficient management of all of our resources. To do that, obviously, it needs to track those resources. So in each of our chapters, we're going to learn about all these different data structures that we use to track the resources the operating system's interested in. Prime example being the process control block. It has all of the resources and things we need to know about in order to manage a process. Open file table entry, well, that tells us everything we need to know to work with one of the files we have open. If we want to know how to go between pages and frames, right, we have the page frame table. When we access a file on disk, right, we're going to have maybe more things than we've listed here, right? This is a bit of a trickier one, but we're going to have, an inode, we're going to have file metadata, we're going to have all the different things we need to know about which one of our file systems that file's in, and perhaps the types of functions we need to talk to that file system. There's going to be all kinds of different metadata we have to keep on that. Likewise with I/O requests, as we saw last time, they're going to have kernel buffers, we're going to have host side controllers that we need to read and write to, all kinds of things we need to keep track of, registers to read from, all that. So we're going to have plenty of different examples of metadata or bookkeeping where it's our operating system's job just to keep track of what's going on so it can try and manage things efficiently. Maybe another good thing that I didn't list here could be like wait queues, right? Who's waiting for what kind of events? Which processes are waiting for what kind of events? That would be another important type of metadata or bookkeeping ROS does. So let's use the PCB as a bit of an example, right? It's a classic bookkeeping structure for a process. We looked at it as though it was some big table with all these different entries and maybe subtables and all these things. That seems maybe scary, but in practice, when we're implementing it, right, it's just a struct. It's a struct. We've got maybe a PID, perhaps we've got a state here, right? We learned running, ready, blocked, terminated, and new. new is the other one, maybe not listed here. And then it's going to keep track of all of its internals, its registers, so program counter and all of the accumulator registers. Perhaps it's got a priority for a scheduling algorithm. We need maybe the information about the page table, right? We said we're probably going to store our page tables contiguously. So we'll have a page table base and potentially a page table limit if we don't have those valid bits. That's another way of telling if we've overflown the pages that we should be touching. And then we have maybe an open file table pointer, right? We learned, or we will learn about the open per process open file table and how we interact with files. We'll have a UID. I'm sure there's plenty of stuff I don't list here, right? Maybe these pointers shouldn't be integers. Sorry. Again, I threw this together pretty fast. Probably this is going to be an actual pointer to something as opposed to, well, page table base is probably fine, but the open file table pointer will be a pointer to another struct, which is another bookkeeping, and so on, right? So that's just an example, right? When we're talking about these data structures, we're dealing with C structs. In the spirit of review, since your exams are coming up, I just wanted to remind you about some of the key things we do with the PCB, right? It's going to store references to all of our resources, things like files, but it's also going to store all the information we need to suspend and resume our running processes. So here is kind of just a little throwaway pseudo C code, right? So whenever we want to interrupt a running process, we have to save its CPU registers. So current process here could be the current process is PCB. And here we pass the registers to some function called save CPU registers, right? That'll populate that array of registers along with the program counter so that when we go to restore it, we know what state to restore. So anyway, we'll update our current program counter. Our state might become ready. Our state might also become blocked depending on the reason we got suspended. Or perhaps we could be terminated and we're just waiting for another process to come clean us up. But anyway, our scheduler gets to pick the next process, right? Once we get the next process, we should set its state to running and we get to load its registers, which is just restoring its state before finally assigning the program counter in our CPU to the program counter stored in the next process. That's when you give the control over and let it run. Anyway, just a quick aside on PCBs since we're gearing up for exam review. Now, the last little pattern that I wanted to talk about is abstraction through interfaces. Right, so let's forget about operating systems, and now is where I'd put up a simple question and force somebody in class to explain an interface to me, right? But I can't do that because, of course, I'm at home. So I'll have to answer my own question, right? What is an interface? An interface is a contract. Right, so you've learned about interfaces in the context of object-oriented programming, almost certainly, right? And it's just a contract that describes which functions are available in a certain type of well, I guess object and object-oriented programming, but here it'll be in some kind of system that supports the interface. Right, we don't need to know how they're implemented in order to use an interface, and that's kind of the whole purpose, right? If we don't need to know how these operations or functions are implemented, then we can make an algorithm that's agnostic to the implementation of those of the functions in our interface, right? So we can create many different implementations that all hide behind the same contract, and then many algorithms that use that contract that are now decoupled from the implementations. And so that's how you gain abstraction. And because one of the primary goals of our operating system is providing the user with a convenient to use system, this abstraction is very important. Anyway, so let's look into it. What does an interface look like in C? So an interface could be as easy as just header files, right? We could have different functions in a header file. Two different implementations could implement the same header file, but it can get a little bit more complicated. And I wrote some industrial C code for some applications where we used interfaces, and when we did that, we'd often use structs with function pointers. So we'd have some struct called block device interface, right? Here I'm trying to allude to your I/O devices where we have open, read, write, and close, right? So this is a block I/O device. Here's our interface. You must implement this set of functions. And in the block I/O interface, it's a structure with function pointers. So this is scary, and I mean, we're not going to test you on this, so I won't spend too much time with it. But if you have a structure of function pointers, then we can implement the interface by pointing these, instantiate this struct, create an instance of this struct, and fill in all the function pointers by pointing to the correct functions for your specific block device, right? So we can instantiate this interface. We can point open, read, write, close to the specific device driver for one block device, and then we can use that elsewhere in our code. Right, so this is how we can maybe instantiate an interface in C where we don't have the nice object-oriented system supporting us. And so callers to this structure just needs to know, well, hey, I have this block device interface. I just have to, ask my I/O subsystem, well, what block device interface do I use for this kind of file access? And then it can tell me what open function to call by giving me this structure. Okay, so what this does is it means that our user level applications get to use simple things like system calls, nice little file descriptors, and the open or read, all those nice system calls, these generic I/O requests. We get to use things like logical address binding. These are all little abstractions that our operating system provides for us to make things easier to do stuff in userland. We don't have to worry about all of these tricky little details that we've been talking about in this class, right? You've gotten to third or fourth year or whatever standing you're in without really having to worry about all these details. You've lived your whole life and spent lots of time on the computer, and I imagine many of you haven't heard about pages until now, right? Because our kernel abstracts that all away from us. You don't have to know about these things to write application code. And that's one of the primary reasons we need an operating system. Anyway, so in application code, you're going to say something like read file descriptor into this buffer and read n bytes. Nice and easy, beautiful little abstraction. And now your kernel gets to figure out, okay, what file are they talking about on what device? Do we have a buffer? Is it buffered somewhere? Do I have to actually go to the device? If I have to go to the device, well, now it's time to block the caller. Hey, before I do all this, maybe do we need to check to see if this process has permissions? Am I dealing with maybe a network file system or a local file system? All this stuff gets sorted out for you. You just get data in your buffer. So when we put it all together, right, we're going to see that many of the operating system mechanisms are going to have all three of these little patterns we've identified, right? We're going to have abstraction, we're going to have translations, and we're going to have metadata. And if you look back through the chapters we studied in this class, you'll see these three patterns cropping up time and time again, with maybe a small exception for when we talked about process synchronization. It's possible maybe some of the process synchronization goes outside the bounds of this pattern. But certainly when we look at, file systems, memory management, virtual memory, it's a lot of abstractions, a lot of translations, and a lot of keeping track of device or resource-specific metadata. Right, so, opening a file, right, we call open, that's our abstraction. There's going to be translations going from the path name that we provide open to the correct inode, which will then get loaded into the correct table, and we end up with a little integer file descriptor, which helps us do future translations more efficiently. Then we have, metadata, right? The kernel is going to create and manage and update all these open file table entries in order to keep our nice translation and abstraction ready. Similar with reading memory, right? Our process gets to pretend that it lives in this logical address space where it doesn't have to worry about which physical location on RAM it's actually loaded. And we get these translations being done in the MMU and the TLB with our page table that do this mapping for us. And of course, there's metadata we need to keep track of. We need to know things about each entry in our page table. We keep track of the valid bits, the dirty bits, all that stuff. That's another example of metadata. Anyway, so hopefully kind of the final takeaway from this little talk is if you're studying one of the topics from this class and you're feeling it's confusing or overwhelming, try and break it down into these sort of different categories. One thing that's important for you to know is its purpose. Well, why do we care about this thing? What's it doing for us in the context of our computer system? If you know the purpose, then hopefully you can just identify these next three patterns as they pop up, right? Is this confusing because it's a translation? Well, that's just a translation. So I start with something I know, I use something I have, and I get something I want, right? Maybe this is some big data structure, and this is just keeping track of metadata. This is all just going to be stuff that I need to do the management of some resource. Maybe this looks tricky because really what we're doing is we're making a convenient interface for our users. We're trying to expose a very nice system call, but behind the scenes we have a little bit more work to do. And so you'll see these core ideas cropping up in lots of chapters. So hopefully this little talk helps you in studying and in understanding some of these concepts better. Good luck with the upcoming final.